In this video, we're going to talk about something called logarithms. At this point, you've found the inverse of linear and quadratic, rational, and some other functions algebraically. Hopefully, it's not going to be a big surprise to you that the inverse of a linear equation is going to be another linear equation, or that finding the inverse of a quadratic function is going to be a square root function. Today, I'm going to be talking about logarithms because logarithmic functions and exponential functions are inverses of each other. In order to find the inverse of an exponential function, we're going to need to rewrite it in logarithmic notation. And to find the inverse of a logarithmic function, we're going to rewrite it in exponential notation. So the first thing you need to know is not let the word logarithm intimidate you. Logarithm was coined in Latin as logarithmus by John Napier in 1614. It is said to be derived from the Greek word logos, reckoning or ratio, and the word arithmos, number. A logarithm is literally a reckoning number. Just because it's a crazy word doesn't mean that it's super hard. So please keep an open mind and let's start by looking at some vocabulary. Hopefully you know that what we're looking at is expressed as 2 to the third power. While most people quickly realize that the 3 is an exponent or a power, it's often forgotten that 2 is called the base. And as you know, raising a number to the third power means that we are multiplying that number by itself 3 times. Now what if we knew what we wanted to multiply by, the base, in this case 2, and we knew what we wanted to end up with, the number 8, but we did not know how many times we'd have to multiply the base by itself to get 8. It might look like this. This is logarithmic notation. And this equation means exactly the same as the other one. We would read it as log base 2 of 8 is equal to something. Finding the answer to this question is what it means to find a logarithm. Find the power, or find the exponent, will we raise to base 2 to get this number in the parentheses. In this case, we already know how many times we have to multiply the 2 by itself to get 8. It's 3. It's just notation. Try not to let it intimidate you. If you think back in the day when you first heard f of x as function notation, it's a little bit unsettling at first, but the more that you use it, the less of a big deal it becomes. Well, this is going to be the same way. The more that you use it, the less of a big deal it's going to be. But if you shy away from it, then it's just going to be really, really awkward for a long time. So just try to embrace it, and I promise it'll get easier. Let's start by breaking it down a little bit. First, it's read log base 2. This 2 is the base. And this 8 is what we ended up with. And then this 3, that's the exponent of the power. Logarithms are equal to exponents, or powers. Remember that logarithms, they have bases and what you end up with, and they're equal to power. So if I write log base 3 of 27, basically what I'm saying is, what power do I take 3 to in order to get 27? Well, the answer is 3. The answer is an exponent. We take 3 to the third power to get 27. And that's all this says. Now, if I wanted to rewrite it in exponential notation, the 3 is the base, and the other green 3 is the exponent, and what I ended up with, 27, that's what it's equal to. Now let's try another one. Log base 4 of 16 basically asks the question, what power do I take 4 to in order to get 16? Well, the answer is going to be 2. So log base 4 of 16 is equal to 2. Now, if I want to take this and rewrite it as an exponential, well, I see 4 is the base, so I write 4, and then I see 2 is the exponent, and I end up with 16. So 4 to the second power equals 16. These two equations say exactly the same thing. Let's take a look at another one here. We've got log base, no base. Well, like most notations, there's some shortcuts. If there's no base written below the log, then we know it's base 10. We call this a common log. So basically what this is saying is 10 to what power equals 100? Well, the answer is going to be 2. So log, or we'll say the common log of 100, or log of 100, is equal to 2. All right, so if I rewrite this as an exponential, the base is 10, I know that because nothing's written down there. The exponent's equal to 2 because that's what the logarithm is equal to. And I ended up with 100 because that's what logarithms have. They have bases and what we end up with. So let's go and reverse the process. What if I take an exponential function and then rewrite it as a logarithm? Here I've got 2 to the 5th power. That's going to equal 32. And let's use some colors. Maybe that'll help keep things straight. So if I write this as a logarithm, remember logarithms have bases and what we end up with. Well, the base is 2 and we ended up with 32. And then the exponent is 5. So we would write this as log base 2 of 32 is equal to 5. Let's look at another one. If I have 10 to the 4th, well, that's going to equal 10,000. And then if I want to rewrite this in logarithmic notation, well, I just look and I see, well, I write the word log and I see the base is 10, so I don't have to write it. I know I ended up with 10,000 and the exponent is 4. That's what it's equal to. So it's going to be log of 10,000 is equal to 4. E to the 3rd. What's E? Well, let's take a look at that because it's a special number. E is an irrational number, like pi. It goes on forever and never repeats. It's figured out in a way that we'll look at in a second. The first digits go like this, 2.71828. It's called Eulers Number, after the guy came up with it. This is how you calculate it. If we take this formula, 1 plus 1 over n to the n, and plug in numbers, then what happens is the bigger the n gets, then the closer it gets to this Eulers number. Let's take a look. So if I put a 1 in there, well, 1 plus 1 to the 1st power, that's obviously going to be 2. And then you can see here, if you did this, we would end up with 2.48832. And then if we did this last one, it gets 2.71815. You see how it's getting closer and closer to this Eulers number. Well, let's take a look at it and see if we can't make it go even further. Okay, so let's first start with the 10,000. If we do 1 plus 1 over 10,000 to the 10,000th power, we get what they got, 2.718146. Now, let's go ahead and make that a little bit bigger. We'll make it 100,000, so we'll add a 0 to each one of these, and you'll see it gets 2.71826. Now, another 0, and it gets 2.7182. Okay, now write that down. And let's look. There's Eulers number. Do you see how it's gotten really close to Eulers number? All right. Now let's take a look at the original question. And we said was e to the 3rd power. Well, e to the 3rd power is 20.08554. Most calculators have an e button. And you see if I take 2.718282 to the 3rd power, I get the same answer. So e is a number. And it's going to be, in this case, we'll have to approximate it to 20.09. Now, if I want a logarithm that's got a base e, it's got a special notation. It's ln. It's called a natural log. And again, like the common log, you don't have to write the e. So if you see ln, the base is the number e. In this case, it says e to the 3rd power is equal to 20.09. I'm going to end the video here because I want to take a minute and have you practice some of this notation, because the problems we're going to end up doing, finding the inverses of exponentials and logarithms, it's really not very difficult as long as you're comfortable with this notation. So after you're finished with this, then you can go on to part 2. Thanks for watching. Hope that helps.